Insecticide resistance arises through a selection process operating over several generations. Insects or plants most likely to be killed by pesticide applications are called susceptible. Susceptibility changes occur to offspring having characteristics passed on to them from their parents. Resistance is genetically based and therefore is a straightforward process of natural selection. Insecticide failure is not always caused by resistance. It may be due to inadequate coverage because of incorrect dosage or spray volume due to incorrectly or poorly calibrated application equipment, clogged nozzles, inefficient pumps, and inaccurate speedometers can all contribute to improper coverage. And new or unfamiliar formulations, incorrect preparation techniques, environmental conditions such as wind, rain, or light can reduce exposure to the necessary quantities of chemical. Insecticide resistance must be verified with laboratory or controlled studies. Resistance to an insecticide, in scientific terms, may be defined as the ability of an insect population to survive a dose of poison that is lethal to the majority of individuals in a normal population of the same species. Resistance may also be defined as when the failure of an insecticide to control a population of insects is due to a genetically transmitted capacity to tolerate more insecticide than is normal. Scientists often refer to the LD50 of an insecticide in measuring and comparing relative effectiveness of the product. The ratio of the LD50 values between suspected resistance and known susceptible groups of insects give an idea of any developed insecticide resistance within the population. From the scientific viewpoint, resistance is a shift in the LD50 performance of a compound, or the lethal dose required to kill 50% of a pest population. In practical terms, it takes more and more of the product to control the population, and it becomes only a matter of time until insects are immune to the effects of the insecticide. Laboratory testing compares the suspect field population with a known susceptible strain. Standardized procedures are used for consistent results. Differences in susceptibility of different life stages must be taken into account. Results are usually expressed as the ratio of the LD50 values between suspected resistance and known susceptible groups of insects. Resistance is most likely to develop when heavy use of an insecticide or insecticides with similar mode of action are used. It can also develop when a use of insecticides has a long residual. A significant percentage of the pest population is exposed to pesticides. Agricultural crop pests, greenhouse pests, and public health pests. Some resistance mechanisms include detoxification, target site insensitivity, slower rate of penetration, storage, and avoidance. Detoxification involves the ability of the insect to chemically modify the insecticide. Considered the most important and widespread resistance mechanism. In several cases, specific enzymes have been identified that assist with the necessary chemical reaction. Target site insensitivity is the site of action of the insecticide is no longer susceptible. The insecticide is broken down no more rapidly than the susceptible insects. Some cases of organophosphorus insecticide resistance are known to operate this way. When dealing with a slower rate of penetration, synthetic insecticides must penetrate the insect body before they exert any toxic action. A reduced rate of penetration may allow the insect to detoxify the insecticide rapidly enough to prevent itself from receiving a lethal dose. Some insecticides can be stored in certain body tissues, such as fat. This prevents the toxin from reaching its target site. This is a contributing factor, but it is not usually an important one. Avoidance is also called behavioral resistance. It is when the insect has the ability to avoid contact with insecticides. It is known to occur in some insects such as mosquitoes. Insecticide resistance due to a slower rate of penetration implies that the insecticide moves into the insect slow enough to be detoxified before it builds up at the site of action. Insect resistance due to storage implies that an insecticide can be stored in a place or in a tissue that is not affected by the insecticide. An insecticide may be managed through insecticide rotation, which involves the alternating use of different chemicals with different modes of action. This practice often delays the onset of or mitigates existing pest resistance. Different insecticide classes may have different effects upon pests. It is important that the user review the particular product label regarding methods to minimize insect resistance to the insecticide. Manufacturers may suggest that no more than a certain number of consecutive applications of a pesticide class be made before alternating to a different class. This suggestion is intended to extend the useful life of the insecticide. Tank mixing insecticides is the combination of two or more chemicals with different modes of action in order to improve individual insecticide application results. This practice may help to delay the onset of pest resistance. To reduce the potential for insecticide resistance, leave untreated areas for susceptible insects. Don't rely on insecticides alone. Begin adopting integrated pest management techniques such as cultural controls, physical and mechanical controls, biological controls. Apply insecticides on an as-needed basis instead of traditional preventative programs. Make sure to follow the manufacturer's labeled recommendation for dose and application. Avoid broad-spectrum insecticides. Use those that are more selective to the pest in question. Monitor insect populations in the field. Employ the use of economic thresholds for insecticide treatments. Protect beneficial insects to elicit their help in controlling pests. Avoid repeated use of the same insecticide. Use insecticides with shorter residual. Rotate between insecticides with different modes of action. Rotate between insecticide classes. Use newer classes of pesticides in a rotation scheme.